Yeah, I was just saying, I think we should start. If that's, I
Yeah.
don't think anyone else has joined. No one's joined. So, um, Ahmed, if you have any questions from the material covered on Monday, how did that go? Because I didn't attend that session. So, how was that? How was that for you?
Okay, yeah, the material was okay, and thanks for Diana for fixing my problem while we are trying to do scale production.
No problem.
Perfect.
Yeah, it's just that my own contour scale contour couldn't finish, and I waited. The calculation was not able to complete, so it was the calculation failed.
Uh-oh.
Yeah, and I tried to repeat it several times. Like, I don't know, maybe there is a problem with that. I'm not sure, but I think
Yeah,
we
so
can.
yeah, what I would like to do is then to check if you could send me that specific file, I can check it. I think Dira sent the finished file that I completed, and you
Yes,
should be able to have that.
yes, you do have it.
Great. Yeah, so we have to start looking for differences and see what could be causing the issue.
It's okay. It's okay.
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 Okay. Perfect. So, in terms of everything else and the content, the speed of delivery, everything was good, and you're happy to carry on in the same way today?
Yes, it was perfect. We can carry on. Yeah.
Excellent. That's good to hear. Well, I think in that case, if there's nothing else, Diana, I'll hand over to you. I'll be here quietly in the background. I'll leave you to it.
Okay. Thank you so much, Samir.
No problem. Okay.
Thank you, Ahmad, for being here today. You're my only one today. That's good. That's good because if you have questions, we can just go through all your questions. So that's good.
Okay.
Okay, so this is the file that you should have for today. Let me just get this also out of the way. And last time we finished the two contour plots. So what I'm going to do is just to finish, just explain the results, and then we can move on with the next calculations.
Okay.
Okay. So let me just bring, where was it? Here. Okay, so this one was for the Olympus contour, and we learned how to bring the reservoir fluid to this specific object, and then we set up the conditions, minimum to maximum for temperature, minimum and maximum for pressure, and the increment. So as you can make the plot very refined if you decrease the increment. So as we put these ones last time. If we wanted to run faster, we can just put bigger numbers in here. And then, as is the usual practice here, we just turn the standard solids on. So once that is done, then we have in here the final results. This is the plot. The default plot is usually this pressure versus temperature. It always will it will always plot the total solid concentration in milligrams per liter. So this is basically the total amount of solids that are going to precipitate. And this value that you see here, this value is also known as the maximum mass or excess solute. So internally at OLI, we call it total solute concentration, but this is the same value as excess solute. Basically, this is the amount of material that can form from solution at equilibrium. Okay, so we have several coloration here in this nice plot. So we see that at high pressures and high temperatures, which is, let's start with high pressures and low temperature. That will be this upper left corner that we see here. You see the small amount of solids that are being formed, about 6 milligrams per liter. You can see the value here in this gray box in here. You can see it. when you have over. So you have a value of around 6 milligrams per liter. Now, if you go at high temperatures and low pressure, so that would be this red part, you see here, the bottom right corner, and that is where you have the highest risk of a scale. And again, if you, however, you see that the value is around 330 milligrams per liter. And the other corner that you will see is also high temperatures and high pressures. So it's this upper right corner, and this basically represents the reservoir conditions. And notice that in these specific reservoir conditions, you don't have formation of any scale. And it's because we define it that way. We said that at reservoir conditions, everything was at saturation, or we saturate. Yeah, basically we said that we had saturation in this. So you don't really form any solids. Now, once you have this plot, another thing that we have seen that clients usually do is that they overlay the production profile. So if you have a production profile, they will overlay that production profile in this plot, and they will see if there is a high scale of risk or not. Okay, so this is for the total solid concentration. You can also study the effect of temperature and pressure on other properties. For example, let's say you also want to see the effect on the pH value. So how do we study that? So you also have the option here, same as the plot. You go to variables, and this will open this new window, and you will see that by default, x-axis is always temperature and y-axis is always pressure. And you'll see all of the possible variables you can plot. So if you want to plot pH, then you always need to go to this additional stream parameters category. You expand it. So in here you will see all the several properties, density, ionic strength, etc. You want pH. So I will double click on this specific variable to replace the previous variable that I have in there, and then you can click OK. Okay, so now you see that the plot is all in green, but this is not because the pH is being constant at all. The reason is because if you notice, the range is going from 0 to 14. So the default pH range for this plot is going from 0 to 14, but this range is too wide, so maybe our pH is between 5 and 6 or 5 and 7. So that's why we are seeing all green. So we need to refine this specific legend or this specific range for pH. And what you need to do is you just go to the options button. And in there, you can go to the contour to the contour variable, and then you have two options. You can use the minimum and maximum button, and for auto, so the software is going to detect the minimum pH and the maximum pH, and just click apply. So now you start seeing a change in coloration, but when I was running this specific plot, I noticed that there is a coloration here in red. Most likely it could be, and I need to confirm this, if it's a calculation error. So this is kind of changing my pH range. So what I need to do to see even better this plot, I'm going to just remove the auto, and I'm going to start playing with these variables. You can say, okay, my minimum pH could be 5 and my maximum pH could be 7.5. Then you click apply. Now you start seeing even more coloration. But let's say that's not enough, so maybe 5.5 and 6.1 for maximum. Usually, ideally, the auto, if we didn't have this calculation error, it will just go by default. But we also have the option to move the values or put the values that we're preferring here. So this gives us a better pH range. And now you can see that different colorations. You see now red indicates low pH values, and this blue indicates higher pH values. So we clearly see that the pH is varying as a function of temperature and pH. For the upper left corner, my left here, we see that the lowest pH values, if you go to this corner, is around 5.5. Okay. At the bottom of the plot is low pressure and mostly all temperatures. You see this blue color, and you can see that is the highest pH values. They are around 6.1. So you can see, you can just basically see the effect of temperature and pressure on this variable. Now the question is, what could be the causing the pH to vary? What's happening in the system? So we know that in this reservoir, our produced water had pretty much two acid sources. We had H2S and CO2 content in this water, in this produced water. And we also had a base source that was bicarbonate. So we know that as we increase the temperature, gases don't stay dissolved in water since they evaporate out. So what we should see, for example, as a pressure, like a specific pressure, a constant pressure, is that if we increase the temperature, now the pH should increase because we are evaporating the gases out. So we started with 5.5, and if we start moving to the right, increasing temperature, now it's 5.7. Okay. And likewise, now let's say you start increasing your pressure. Now that means that the gases will remain dissolved in solution and the pH should decrease. So let's say we are at 90 degrees C, we start at 6.1, and then as we increase the pressure, now the pH is 5.6. So that's how you...
Diane, I'm sorry to interrupt you. I've just noticed, I'm not sure if you have, but James has joined us.
Oh, yes. Hi, James. Sorry. Sometimes I get into the presentation here and I don't notice the...
No problem. And also, while I've interrupted you, there is a bit of an echo on the line when you're speaking. So for me, it's not a problem. But if anyone else is having any problems struggling to hear Diana, do let us know.
Okay. I kind of hear it as well. Last time I was also hearing it, but I think I got used to it.
No problem.
Yeah. Okay.
I can see James is on the audio, but I'm not sure. Can you hear us, James?
Yes, I can. I can hear you guys.
Okay, perfect. All right, excellent. Yeah, sorry, Diana.
Put my chat here. Yeah, I put my chat in here, so I won't miss any. Okay, thank you, Samir.
No problems. Carry on. Sorry.
No problem. Okay, so that was with the pH. Any questions about the pH or variable or how you analyze these plots? I will show 3 more different variables. Just because I want you to be comfortable analyze. I think this plot is very useful and it's really nice to understand how you can play with it. So we were discussing that the pH could be directly related to the solubility of gases in solution. We were saying if we increase the temperature, the gases evaporate out. If we increase the pressure, then the gas solubility increases. So we can also understand the solubility, let's say, of CO2 in this water. So we can go to the variables button and we can find, we want to plot the solubility of CO2 in this produced water. So what you're going to do is you go to liquid 1. Liquid 1 stands for aqueous, the aqueous phase or the brine phase. So then you just expand it and look for the CO2 liquid 1. So we'll click on it and change the variable and then click OK. Again, we are having the same problem with the range, and this red square here probably is causing some issues, but it's okay. We can go to options, contour, and change these values. Let me find out which values do we need. So we have minimum value. Let's say we have 100 here, maybe. And we apply. Oh yeah, good. So if we put 105 in here and 800 in the maximum, then click apply, and now you will see this plot. This plot, it looks very similar to the pH plot that I previously presented. So you could argue that what is causing the changes in the pH is the solubility of the CO2. Okay, as the CO2, as the pressure increases, solubility of CO2 increases, so then you have a higher content of CO2 in the liquid. And as the temperature increases, then you have less CO2, and then you will have less amount of CO2 here, and then you will also have a higher pH. You could also argue that what is causing the formation of a scale, when we saw at the beginning, we had this plot that it was all red in here, and it was increasing from low temperatures to high temperatures. You could argue that the CO2 in the water is what, or the solubility is of CO2 when we are changing it, is also causing the formation of carbonate or calcite in the system, because as we increase the temperature, we have less CO2, and that means that the pH increases, and as the pH increases, the carbonate ions become more stable, and hence it causes the precipitation of calcite in the system. And finally, I just want to show something here really quickly. Maybe you want to know specifically how much calcite you have. You go to the solid category, and then you go select calcite. Again, this point here. So I have down here 360, and I have 0. So we can plot that contour. Let's change this from 0 to 360, 380. Now you see, this is the amount. This is 0, and this is the maximum amount of calcite that you will have in the system. And you can also understand barite. And in here, it seems that there is no calculation error, so we can definitely use the minimum and maximum automatic button. And you can see here how there is the change or the production or the formation of barite as temperature and pressure changes. The maximum amount of barite you see that it is formed at low pressures and low temperatures. And we don't have any barite at high temperatures and high pressures because is highly soluble at these conditions. So the conclusion, and basically, I just want to mention is that the purpose of this diagram is that it allows us to look at the trends of the fluid chemistry as temperature and pressure changes for any variable you want. Okay, any questions at the moment? With this, I will just move away from this contour, and then we will continue with our Titan. We will finish our Titan reservoir that we got started last class. Okay. Perfect. So, okay, so last time, what did we do? We created our brine analysis. The difference, or the different things that this water analysis had was that we had iron content, that we have some acetate concentration, and that we also had boric acid. We also added our Titan gas, and this Titan gas didn't have any H2S content. For the Titan reservoir, then initially we brought the brine and the gas. We defined the flows and the conditions at the reservoir. We turned the solids. We didn't do anything with the solids. We didn't turn any solids on. We calculated, and we saw that the values for the pre-scaling tendencies, it showed that calcite was nearly saturated, like at 75%. So we decided that we are going to saturate with calcite. Was it calcite? Yeah, it was calcite. So we decided that we are going to saturate with calcite. And then the geologist, a geologist told us, no, this reservoir, it has a lot of siderite, so we are going to saturate with siderite, and we said, well, let's do barite as well. There is a high chance to do that. So we selected these 3 different minerals to saturate. We selected barite as the influx to vary for barite. For calcite, it was sodium bicarbonate, and for siderite, it was iron chloride. And Ahmad, I also asked the question to my colleague that he's he has more expertise about these calculations, and I asked him the question about why did you use here 2 different chemicals or 2 different flows in here instead of using calcite. The answer is 2 reasons. Let's say if you use calcite or carbonating here and carbonate down here for the siderite, so you are having in 2 places you have to vary the carbonate, and then you're moving 2 variables. So that may cause a calculation error, or maybe never converges. That's one of the reasons. And the other reason is because the software is allowing you to select not only the same stoichiometry of this calcite or siderite, you can select some other chemical as long as you put, like in this case, you want to saturate calcium carbonate, so you just use sodium bicarbonate in this case, and in this case you also, for siderite, you wanted to match the iron content, so then you will select iron chloride. So that's what I found out yesterday, if that answers better your question. Okay, so yes.
Yeah, thank you for that.
No problem. Yes. And once we saturated with these 3 solids, then we came here to our pre-scale and post-scaling tendencies. So we confirmed everything was saturated. Then we realized that we were adding way too much calcite. We said, maybe not, maybe this is not a very good idea, because this will change our chemistry very much, by a lot. And also, actually, I don't know if I explained that. Maybe I should just go ahead and start with that explanation. So let me bring the presentation before I assume I explained something that probably I didn't. Yeah. Yes. Okay, so let's continue here. So once we saturated with these 3 solids, then we go to the report tab, and then we realize, okay, the software is saying that in order to reach saturation with this barite solid, we have to add 14 milligrams per liter to the solution of barium sulfide. To saturate with calcite, the software has to add 495 milligrams per liter. And with siderite, it will be 14 milligrams per liter. Okay, so this will definitely have an impact on the alkalinity value, for example, this calcite here. So we should really wonder if that's really the case, because this is a big change for the chemistry. So for this calculation, we also enable the alkalinity calculation, and we see that this alkalinity, the new alkalinity, is 560 milligrams per liter of bicarb. And also notice that for down here, if we come down here for the brine composition, notice that now my iron concentration initially was 2, my brine analysis, and now it's going up to 8 milligrams per liter. So this is 4 times more than it was initially measured. Barium concentration was 25 milligrams per liter, and now it's 32. The new value is 32. So the question is this reasonable? Because this error is around 22%, and is it possible that we have an error of about 22% in our measurements? That's something that we should ask ourselves. And regarding the bicarbonate, so our bicarbonate now has a value of 755 milligrams per liter. And if you remember in our Titan brine, when we calculated the bicarbonate concentration, if you come here, that bicarbonate concentration is around 355. So now we are saying by saturating with sodium bicarbonate, my new bicarbonate concentration is 755. So that is almost 400 milligrams per liter. Almost, yeah, that's way too much. So maybe this value saturating with calcite is unreasonable because it's not possible that the laboratory results are off by this much. Okay, so we should basically now say, okay, is it a good idea to saturate with siderite? Is it a good idea to saturate with barite? Is it a good idea to saturate with calcite? So I would say with siderite and calcite, probably not. I don't think that we should increase the concentration of iron by this much. And I don't think that we should increase the bicarbonate by this much. This is not a representative fluid. You know, like it's not really representing what it was measured. But we could say, okay, only the mineral that may be a borderline to saturate could be barite. Maybe we should saturate with that because, you know, usually we will have formation of barite. So we will if we include the barite, maybe we can just account for the worst scenario. So for this example, maybe we can run two cases. We can do no solids. We don't saturate any solids, or we can just saturate only with barite. I'd say that for training purposes, I will saturate only with barite, and so we will account for the worst case scenario. So let's go back to the design tab, and now we delete calcite. That was not a good idea. And iron carbonate or siderite, delete it. And once you delete those values, then recalculate. Okay, so I think that this will give us a better or the most representative fluid for the Titan well. And that will take us to the next calculation. Once we have our representative fluid, now we can go to our scale scenario step. So once the calculation is completed, we can create our scale scenario. Oh, let's go really quickly to the report to see how much barite was added, the same, 14. And now we see that our bicarbonate is, I think this is the original value, and also we don't have very much change for iron. It's 2 milligrams as measured. And we also have, what else it would change? I think that's it. I think we didn't change very much. So that's good. Now, double click on the scale scenario. And let's rename this scale scenario as Titan production. So in here, what we are going to do with this object is to study the effect of temperature and pressure on the properties of the reservoir fluid. And we will see, we will increase or decrease the risk of scaling at different locations. So we are going to bring here the whole fluid, Titan reservoir that we just created. And we will select automatic flow. By the way, let's save this file, save as, and let's put day 2 so that we divide this. Okay, once we enter the whole fluid, then we go to conditions. And for these conditions, we are going to enter the conditions for Titan production that I have in here. is 7 different locations. I'm going to copy these values and paste them. So we have the different locations are current reservoir, goes to perforations, 2,000 meters, 1 meter wellhead, slug gusher, and separator. And the recurrent reservoir stands at 160 degrees C and 470 bar. And please let me know when you have entered this data. Okay. Matt, is it? Let me know whenever you have the data entered.
Okay.
Is it done? Yeah, the next step is just to go to the solid step. It's always our third step. And we select the standard solid. And that means that by turning the standard solids on, we are allowing to any of these solids to form in case they are supersaturated. So if they become supersaturated, they will precipitate out. Let's go ahead and calculate. We can always, while this calculation goes on, we can just click on the plot tab to see how, well, just to see how the software is calculating each point. And our next step will be basically to interpret these results. I have my calculation window here. Perfect. So what are we seeing here in this plot? So what we generally want to analyze is the scale risk. So we will take a look first to these pre-scaling tendency values. And then we will change this plot to see the amount of solids that may have precipitate out. So again, default plot, dominant pre-scaling tendency versus locations. We see that all of these solids down here, they're not saturated, they're subsaturated. And the only solid that is supersaturated is barite. And let me change this again to the left. Maybe it's better that way. So we see that barite becomes supersaturated as the fluid moves through the different locations. So it starts at 1 because we saturated with barite, reservoir conditions. But as we are producing this fluid, the scale risk starts to increase and increase and increase until it reaches to the separator where it has a value of around 4 for pre-scaling tendencies at the surface. So we know that barite is the only one that is precipitating out. Okay, we can really get more out of this plot. So the next step is just to see how much material we can potentially form or precipitate at each location. So let's see the amount of solids that form. So to do that, just go to variables. Oh, actually, last time, I think that we created in the plot template manager, we should have created a plot that was called pre-scale and solids amounts. Do you have that plot? Maybe because I sent it to you. If you have the file that you have, probably you will not see it. But if you have it, you can just click on that pre-scale and solids amount, and immediately you will see the formation. You will see that in the Y2 axis, we have the calcite and barite solid formation. So I don't know, Aman, I don't know if you, for example, you have that access to that plot template manager. If you don't have access to the plot template manager, what you need to do is just go to variables And in the Y1 axis, what we are going to plot is the prescaling tendencies for calcite and barite. Okay. And
Okay.
for the Y2 axis, we are going to select solids, and we are going to select calcite. Probably you won't see calcite because it's not forming, and barite will be the one. But yeah, but if you have in the plot template manager the one that we created last time, prescale and solids amount, you will be able to just click on it and you will see this plot.
Yeah, I have it.
Oh, perfect.
Mm.
That's good. So what is this plot saying? This plot is saying, okay, calcite down here, this is the amount of solid that, no, this is the prescaling tendency, subsaturated. And as a result, you see that nothing is being formed, 0, 0, 0, 0. For barite, so barite is this prescaling tendency that we just saw. But the blue line is saying this is the amount of solids that we are forming. At separator condition, at separator, you will have 36 milligrams per liter of barite being or barite precipitating out. Okay. So the combination of these prescaling tendencies, and you can also see it as a view data here. So the combination of these prescaling tendency values and also the amount of solids that you're forming, this is what you will provide to a chemical supplier or to the operator, and they will quantify the risk, or at least create a qualification of the mineral risk that they may have. And once again, OLI doesn't really do the part of suggesting, like if you need to decide what is the scale inhibitor and what will be the best concentration, it could not suggest that part. We are planning to do that probably in the next 2 versions of the software, but at the moment we can't do that part. Instead, what we provide to you is these amounts, and then you can move and basically try to assess the risk of scaling. So this is the Titan scaling scenario. Any questions so far? Let's go back to the plot. And then let's save just in case. And then the next step is just to create the contour diagram, which we already did. We should have it all created here. My plot got deleted, and I don't know why, but I can just try to open here the training one and see if it, yeah, this is it. So you should have obtained a very similar Titan contour. So again, you just double click on the scale contour, go to design tab, bring the Titan reservoir, set up the conditions, select the solids, and calculate. Once you do that, then you wait a period of time, and then you will have this specific contour diagram. Okay. So what you see here is basically very similar to what we saw for the Olympus plot. You can see that as the pressure drops, this is as the pressure drops, the scale concentration is computed to increase at higher temperatures. We have actually, yes. So we see that we have high temperatures here. And we start seeing also that we start decreasing here this pressure, and the scale tendencies also starts to decrease. So it's very similar to what we saw before. Probably could be inferred that these conditions probably were forming calcite or siderite or both. And the formation of a scaling at low temperatures and low pressures is probably barite. And you can also play with these variables to come and see how much calcite you're really forming. You have this plot. So yeah, basically the solid formation that we saw there is mostly calcite. You can also see if there is a little bit of siderite. Yeah, it is a little bit, around 20, less than 20, or around 20 milligrams per liter. And you can also see probably barite. Then you apply. I don't like this specific coloration here, but you can see how it changes. The lowest will be at reservoir conditions, basically no formation of barite. As you decrease temperature and pressure, then you will have more formation of barite. So again, this is very similar to the contour plot that we previously saw. Okay. Perfect. So that means that we have ended the calculations for our two reservoirs that we did, the Olympus brine, for the Olympus reservoir and for the Titan brine. And so far we have covered the following objects. So we have done brine analysis, gas analysis, saturator, scale scenario, and scale contour. We haven't covered so far. We haven't learned how to use the oil analysis or the mixing water object or the add facilities object. So the next object that we are going to learn how to use is the facilities object. So with these facilities objects, it will give you the option to, or the ability to create a process to simulate production facilities. And what we are going to do to use this object is that we are going to mix the two different wells that we have previously created and add different blocks that represent production at the surface. So in this example that I have here, we have 14 blocks to represent production. We have the Titan well. It's flowing from the reservoir to the wellhead to the choke. Simultaneously, we have the Olympus fluid, okay, flowing from the reservoir to the well into the choke. And both of these fluids meet at the gathering location, which is the manifold. And then the manifold flows into the flow line. And then the fluid makes it to a separator facility, where it goes to this high pressure separator. And at this point, the gas and the water are removed. Let me just put this pointer. At this point, the gas and the water are removed. Then what remains flow through a low pressure separator, where once again the gas and water, if any, are removed. And the remaining oil or condensate goes to this oil heater. And in this oil heater, any remaining water or oil or gas is also separated. Okay. Then the oil goes to the oil treatment facility. The water was removed from the HP separator, LP separator, oil heater, gas treatment, and oil treatment go to the water disposal stage. And also the gas that we got from HP, LP, and oil heater, it goes to the gas treatment facility. So we are going to build this process that can be seen as a series of mixers and separators. And with this process, we will be modeling what happens when we have more than one fluid that is being processed at a given time. We will also be calculating the scaling, if there is risk of scaling and other properties across these production facilities. So let's start building this. So the first step is to add the facilities object. So double click on it. And this creates, let me just go back to my date. This is day 1. I'm going to close this. So double click on this add facilities and change it to top side. Ahmad, do you have a question? I hear you were talking.
No, sorry for that.
No problem. No questions?
No, I'm okay. So we can continue.
Okay. So then when we add the facilities object, then label it top side. Okay. Now you will see 3 different subtabs, very similar ones, but now you are going to see this one is inflow specs. And this tab shows a screen with what we call a node diagram. And we will build each node at the bottom of this screen. If you see here, here is where you define basically the conditions of this node. This node will be basically each one of the steps I showed previously in the slide. So we know that we had 14 different stages. So we are going to add 14 different nodes. How do we do that? So if you come down here to node input, let's add 14 nodes. Click maybe 13 times until you reach node 14. So for each node, we will add conditions, we will add inlets and outlets, and we will also be able to separate gas and oil and drop solids if you want to. Okay. So once you have these 14 nodes, now we have two options. We can just double click here and give it a name for the different locations, and then enter temperature and pressure here and the flow. Or, which I find it easier, is to go to the conditions tab. So if we go to the conditions tab, in here, we can also change the name and put temperature and pressure for each specific node. So again, because I know this is time consuming of entering each one by one, and also maybe we have some typing errors, we can just go to the facilities, Titan, Olympus in the Excel spreadsheet, and we can just copy the names and temperature and pressure. And we paste it under name node 1 and Control V. And now we should see this. We should see the conditions at the Titan reservoir, and this should match. These values should match to what we entered here at the Titan reservoir. We have the Titan wellhead, choke. So we enter here first my Titan, then the Olympus. Now where they meet, manifold. Okay. Flow line, separator, and etc. So let me know whenever you have this done. We can move to the next step.
I'm done. You can continue.
Okay, thank you. James, are you done with this step? Let me know. Perfect. So far we have entered the names and the temperature and pressure for each node. Now we need to define the type of fluid we want that it needs to flow from each node. So we are going to go back to the inflow specs tab. And notice that now everything is refreshed. Now we have every single name. And we also have the temperature and pressure entering here. And as I said, we need to define the type of flow. So if you click in the Titan reservoir, for example, which is already selected here, notice that, you have this option here. So now what we need to do is to enter the fluid, what type of fluid. So for this specific one, we need to enter external flow because we haven't really defined what will be entering in here. So what we're going to do is under type, go and select the drop-down arrow and select whole fluid, Titan reservoir. And again, it will be automatic. Okay. again, this makes sense because what we are doing is taking external stream. We're taking the Titan reservoir contents, we are taking it into this new node, putting it, you see this arrow here indicating that it's an external stream. And okay, so that means that we have added this external stream. Now, the next node will be Titan wellhead. Okay, and in the type section, we go back to the type section. And in here, we need to select. Well, you will see different options. You will see whole fluid, brine, oil, gas. You will also see brine from, oil from, gas from, and whole fluid from. The last four ones that say from, that means that they are internal streams, meaning that the material is coming from the previous node. So whenever you see this from, it means that information is going to be taken from any node that was previous, that was before the node that you are defining. So select the option whole fluid from, and now the software will filter the names that are only coming from nodes, and then select Titan reservoir, and then calculate. And then in the flow it says calculated. Okay. And the next step is to click on Titan choke. And again, we are going to say whole fluid from internal stream comes from the Titan wellhead. So we look for Titan wellhead and it says calculated. So now what you see here is, you see how the material starts moving from left to right. Okay. So I think this is a good time to take a break for 5 to 6 minutes. So why don't we go back, come back, I always have a hard time with this, 2 minutes after the, yeah, here is 9:56, so it will be 2 minutes after the hour, and then we can continue with the Olympus reservoir and continue creating this facility subject, okay? So that will be my 10:02, and probably will be your 4:02, Amat. So we'll take a quick break.
Okay. Yeah. Okay, sorry, I'm trying to reach the storage. Sorry.
Okay. Hope you went for coffee, tea, something to wake you up. So I see Ahmad here and James.
Yes.
Great, good. Okay. So let's continue building these facilities process here. So we finished the part of Titan. Now let's click on Olympus Reservoir. And again, in this case, we are not going to get an internal stream. We need an external stream. What you can do is, since this is Olympus, you can go to Olympus Reservoir and just drag it into Olympus Reservoir here. We'll see here that it will immediately create down here whole fluid, Olympus Reservoir, pneumatic. Or you can just come here and just do it manually. Doesn't make a difference. Then click on Olympus Wellhead. And we're going to get internal stream this time. So we are going to go and say whole fluid from. Then it comes from the Olympus Reservoir. And, oh, I selected gas from. No, I want whole fluid from Olympus Reservoir. Then we go to Olympus Choke, and then we do the same. Whole fluid from Olympus Wellhead. Okay. Now, we've got fluids exiting the chokes at, like from Titan and Olympus. And we are going to click on the manifold and get whole fluid from both of these locations. So for manifold, you select whole fluid from, and select the Titan choke. And then for the second one, you just select again whole fluid from an Olympus choke. So you see now that this flows to manifold and this Olympus flows to manifold. Okay. So everything comes here. And the next step is go to the flow line. So it's going to take everything from the manifold. So you come here, whole fluid from manifold. Okay. And now this manifold is going to go to the HP separator. So we are going to do the same. Whole fluid from, it comes from the flow line. We see that specific transfer here to the HP separator. And at the HP separator, at the LP separator, things are going to change. So in the LP separator, we are going to start separating oil, gas, and water. So it is plausible that this LP separator will take mostly oil or condensate from the HP separator. So in this case, we will select only oil from the HP separator for the LP. So click on the LP and go to type and select oil from and select HP separator. So you notice that only the black line appears here saying, okay, only the oil is transferring from HP to LP. Now we go to the oil heater. It's going to get the oil from LP separator. So go to type oil from LP separator. And that's it. I guess. Oh no, this oil heater. So now from the contents from this oil heater are going to go to the oil treatment. Okay. So we're going to do oil treatment is going to get oil from oil heater. Perfect. Now, gas treatment. So what do we have for gas treatment? Or for water treatment? No, yeah, let's go for gas treatment first. So we are going to get the gas from the HP separator, LP separator, and oil heater. They are all going to be at this location. So we get gas from HP separator, gas from LP separator, and gas from oil treatment. Oh, sorry, oil heater. I don't know what, something looks wrong here. Let me see. LP separator, what did I put? No, I don't think I had to put more here. This is gas from, okay, gas from oil treatment. Perfect. Does it look correct to you guys? I'm messing something up here. Let me double check. LP separator comes from oil heater, goes there. Why is this going back? Oil treatment. Oil from, no, that's not going back. This is gas treatment. Okay, I'll double check that. And for water treatment, we have 5 sources. We have, you see the lines here for gas, for water, 1, 2, 3, 4, 5. So those will be all of these will be the sources for water treatment. So we get brine from HP separator, brine from LP separator, brine from oil heater, and brine from gas treatment, and brine from oil treatment. And that should be it. Let me double check really quickly that I'm not doing something wrong here. The gas treatment, the oil treatment to me looks a little bit weird. Let me see. What is that specific file? Don't want to go ahead and do the calculations without double checking this. So for the oil heater, we have oil from LP separator. For gas treatment, we have HP, LP, oil heater. Oh, okay, so for gas treatment, we need HP separator, LP separator, and oil heater. No, oil treatment. And oil treatment will be oil heater, and water treatment will be HP separator. I think this is right. Okay. Let me just say this. So it should be like this. Oil heater. So I think everything started here from the LP separator. So let's confirm LP separator, you should have oil from HP separator. Oil heater, you should have oil from LP separator. For gas treatment, HP separator, LP separator, and oil heater, gas. For oil treatment, that will be from oil heater, oil from oil heater, and for water will be these 5 different locations. I hope I didn't make you confused there. Okay. So that will be the setting up of this specific facility. So the idea is that we are showing, we are building this process here. So that's what we are trying to simulate, building this process. So once we do that, the next step is to go, well, we already went to conditions to make the naming of these facilities easier. Then we go to solids. Then in here, what is common practice is just to select standard solids. In case anything is super saturated, it just precipitates out, and then go ahead and calculate. Okay. So I want to, while this calculates, I want to mention that this application specifically for facilities, it was meant to do only basic mixing and separation with the existing mass that we have in here. However, there is not the ability to split the streams or recycle streams or add any what we call controllers. That will be the domain of the process simulator. And we do have that process simulator, we call it flow sheet. But this is the most that you could do for mixing and separation, specifically in ScaleChem. It will not allow for splitting or doing recycles if you need to. Okay. So once the calculation is done, you can go to the plot tab. And we can start analyzing the results. My computer is a little bit slow, so I will make sure that for my next training I get a faster computer. Okay, now it's not. Okay, I don't know. I think that my computer just got a little bit out of focus here. Okay. I'm sorry. Give me one moment here. Something happened with my calculation. Let me know if yours is done.
Yeah, my calculation failed. I think I've got one of my data points messed up. one of my nodes messed up.
Oh, yeah, it probably was my bad. Yeah, look, I didn't ask, it didn't seem like, okay. Let's double check. I'm going to open a new file. Yeah, my calculation also it also failed. It kind of stopped. Let me open this file here. So let's double check under conditions. Let's double check. No, the conditions, no, in the inflows. Specs. So let's double check that we have everything. I think everything should be fine until the HP separator. So for the LP separator, we have oil from HP separator. That's how we should have it. Oil heater should be oil from LP separator.
Got it.
For gas treatment, it will be 3 gases coming from HP separator, LP separator, and oil heater.
Got that.
For oil treatment, it will be oil from oil heater.
Got that.
And for water treatment, it will be from 5 sources: HP separator, LP separator, oil heater, gas treatment, oil treatment.
Yeah, I've got that as well.
Okay, so in my case, because I didn't save, my software didn't save the top side. So let me see if I can just copy and paste and rerun it with you. I just want to build this case with you. No, doesn't let me. Oh, let me see if I can just do it here.
I'm trying to recalculate here and see if it goes.
Okay. And what about you, Matt? Was your calculation successful?
I'm a bit lost. I'm trying to complete my notes.
Oh, okay. Do you need any help with that? I know that it can become very confusing. Do you want me to put my screen in a specific calculation for you?
Okay.
Okay, so let me just put it here. You want it under which one? HP separator? Oops, I didn't mean to do that. LP separator,
Yes.
oil heater. Did it calculate, James? Did it fail or?
Yeah, it failed again, and I'm trying to. It looks like it's failing at. It'll get green check boxes all the way through HP separator, LP separator, and oil heater, and then it fails. So I'm not getting green check marks on gas treatment, oil treatment, water treatment.
That's interesting. Okay, so what I can do is I will need to check that file and see what could be causing that issue. I could send you this one that I know that it converged.
Yeah, no, that'd be great. I'm not sure where, because my diagram and everything looks exactly like yours. All the nodes are the same, so I'm not sure where it's messing up.
Okay, so could you please really quickly type your email so I will send this to you?
Yes.
Okay. How about you, Emma? Were you able to calculate? Do you need the file? Or you're good?
Yeah, I need the file.
Okay. Is it also failing?
No, I'm yet to. I was left behind actually, trying to
Okay. Got it.
catch up.
I'm sorry. I'm sorry I didn't ask before if you were with up to speed. I think I sent you something yesterday, so I should have your email.
Yes.
James, did you receive the file? Oh, I think I didn't add the attach the file. Now it goes. Perfect. Okay. Yeah, this is a very a very bumpy calculation because it's so many things that you need to understand and make sure that you get it all right. Okay, so let me know, James, when you receive the file, and then if you were able to open it or not, so we can go ahead and analyze the plot.
Okay, I haven't seen it come through yet, but
Yeah, it hasn't. Yeah, I sent it. Okay, yeah, so one of my explanations of where it could be failing is probably around here. Yes, where as you said, James, gas treatment. And you can see that there are no points calculated here, probably because we don't have water content. The software by default assumes that everything has water since we are an electrolyte software. So sometimes when the software doesn't see a little amount of water in the calculation, sometimes it just has a hard time to initialize and get any results. I've noticed that.
what's the workaround for that?
Yeah, one of my workarounds for that in some cases is what I do if I am doing some simulations. I add a tiny amount of water, like 1/10 to the -6, for example. And then I get it calculated, I get it initialized. And if I want to, I just leave that amount of water because it's minimum. Or once it's run, then you delete it and then make it run again. And it takes the latest values. So then it calculates again. That's my workaround.
Okay. So why would, I guess, is your version different somehow that you're working with to where it was able to force its way through there without a little?
My version is this one, the revision 10.01.24. If you go to help about, then you will see revision.
Uh-huh.
You have this revision, the 24 version.
Yeah, I have that version as well.
Oh my God. Yeah, that's very weird. Maybe that is, I couldn't explain why. I will definitely double check why you're having that issue. I will check with the
I've
developer.
got your file now, so I'm good to go.
Perfect. Great. So whenever you have it open to your plot, you will see that the default plot is these prescaling tendencies you see here. In the x-axis, again, prescaling tendencies, y-axis, you will see all of the different nodes that we define, 14 points representing each location. And we basically have 4 different systems here. So we defined the Titan reservoir, the Olympus reservoir. Then we had a mixing step here at the manifold. Maybe flow line could be also considered mixing. Then we had the separation and treatment section. Okay. You can see that after the HP separator, we don't have any water content, as we were discussing, so we also won't see any prescaling tendencies. So we shouldn't really analyze this part at the moment because it's making it difficult to interpret the results here. So what we can do is to zoom in. If you go look to around 12, just drag the mouse and make this box appear, and then it will zoom in for the plots, for the points that we are selecting. Okay, so what can we see here? We knew that the Titan reservoir initially was saturation condition, so it starts at 1. This is barite solid that you see is yellow line. And as we move to the surface, it gets slightly supersaturated. We also see the same thing for the Olympus. It starts saturated at the reservoir and it increases or gets slightly supersaturated above or at the surface as it flows. And then we see an increase in the prescaling tendency values at the manifold. We also see the formation of iron sulfide at the manifold. Now, why are we seeing this formation here? Again, probably this is because we had in the Olympus, we didn't have any iron content, but in the Titan we had iron content, and in the Olympus we had H2S, but in the Titan we didn't have H2S. So once they combine, they produce iron sulfide. Okay, so by mixing it, they are look at the prescaling tendency, it's around 6.75. So it's really causing, it's creating a lot of saturation of this specific solid. And as we continue moving towards the flow line and HP separator, we see an increase of both barite and iron sulfide. Okay, so for the second part of the plot, what we can do, like we had the LP separator and water treatment, we can just click on this button here to see view data, to see the information in tabular form. And you will see that for water treatment, this is what you will be obtaining. You will have 36, a prescaling tendency of 36, which is very supersaturated for iron sulfide, and you will also have a prescaling tendency of 25 for barite. So let's say if you have a treating system where, let's say, is a pond. So both of these solids will settle out at the pond if you are treating the water that way. So you will see the formation of these two solids. Okay. If we go back to view plot, we can change the variables. We want to see the amount of solids that we are forming. We can just click on variables. And then actually, no, I don't think you will have that because you have a new file. So for solids, go to solid, the solid tab, and add barite for Y2 axis and iron sulfide. Oh, I didn't do that here. Barite for a Y2 axis, so use this right arrow here, and iron sulfide for Y2 axis as well. Then click apply. Maybe we can delete, maybe we can, for the prescaling tendencies, let's add only the ones that we're interested on, barite and pyrrhotite. Okay. So what do we see here? So now we see that we have 3 different regions where significant amount of barite precipitates out. So we have the Titan, we have a lot of solids precipitating, up to 20 milligrams per liter of barite. And then we also see that the mixing point, we also see an increase in the precipitation of, or the formation of this solid, right? And for iron sulfide, We don't see very much. We see that it only occurs after the manifold. And it's not very much. It's around 0.85 milligrams per liter. Okay. Now, for this calculation, we assume that all the solids that are being formed here, they will flow, or they will be allowed to travel along this fluid. So we're assuming that there is no adhesion anywhere. So this is something that the software cannot predict for you. What you can do, and there is just a specific feature that we have. If you think that you have adhesion or a scaling buildup, a specific location, what you can go do is go back to the design tab, and then you go to the conditions tab. You will see there is an extra column here saying drop solids. So you can say, okay, at the Titan reservoir, we have that all the solids precipitate out in there. So you can select that option and go ahead, and then you can just go ahead and recalculate and see if that is, if you know that you're having some precipitation there, you can recalculate and see how it changes the results. For this example, I am not going to instruct the software to drop any solids in any location, because by not turning on this option to drop solids, we get the worst case scenario, or worst case for scaling buildup. So it will depend. It will depend on how you quantify your risk. You can drop the solids or allow them to stay suspended in solution. That will be your. It will depend on how you, how do you assess this risk for scaling. Okay, so let's save this document. I don't want to lose any of this information. And this ends the demonstration for the facilities object. I will start introducing the next object, which is the mixing water object. But before I go to that, are there any questions? Yes?
Okay, yeah. This is Ahmed. I'm here to receive your file. Sorry.
You didn't?
Yeah, I didn't receive your file.
Oh, I sent it. 10:20 my time. I will send it again. It's called ScaleChem Training Day 2.
Okay.
The email server might be stripping off attachments or putting it into junk too, if it's got a file attached. So just check in your junk folders and things too, Emma.
Okay.
I will resend it. Maybe it's going at a very slow speed. So I will, I will wait till you receive it, I guess, because then you can continue with the next object, which is the mixing water object. So let me know if you receive it or not. Mine is still saying here, sending messages 1 of 1. So maybe it's taking its time. Let me just really quickly do something here for you, so that we don't lose a lot of time here. I'm going to create a link that you're going to click on it, and then you can download the file, okay? I'll send it in WebEx.
Okay, thank you. I have the file. It's okay now.
Oh, okay. Yeah, I just sent the link. If you don't, it's just in case you didn't receive it. Perfect. Okay, so what we're going to do now, this is the facilities, and we're going to study a little bit, a bit further, the issue that we had about incompatibility that we saw at the manifold. when we mix both the Olympus and the Titan brine. So what we're going to do is we're going to study this incompatibility using the mixing water object. Okay. So this mixing water feature calculates fluid properties when two brines are combined or mixed. For this object, we always select up to 2 brines to mix, and we can also add a single gas or a single oil phase and select solids. Then we will designate whether the mix should take place by a flow rate or a ratio. I will show that later. And the software will change. The software changes the relative volumes of each fluid to create a combined fluid at the selected ratio or flow rate. So the total brine, gas, and oil flow rates do not change during the calculation. Maybe I'm just mentioning all of this, but let's go ahead and just start with the mixing calculation. So, and again, we will use the water from Olympus, water from Titan, mixing the manifold, and then we will analyze the results. So the first step that we need to do is go to the Actions panel and double click on the icon Add Mixing Water. And the next step is double click on it and rename it. Rename it Olympus Titan Incompatibility. It's a long name. Okay, so before we start building this mixing water, we need to know certain information. In our case, we know that we want to study the incompatibility of the manifold, and we know that the pressure and temperature in that specific location is 100 degrees C and 100 bar. Once we know what phases we are going to include in the conditions, then we can start entering the information here. You see first brine and second brine in this inlet step. Okay. Now, once you know the fluids are going to mix, then you select them here. Notice that it says brines. So what that means is that you can only select 2 brines. You cannot select a whole fluid or a gas, nothing like that. It has to be brines. So that means that, yeah, all of the other phases will be included, will be excluded. If we need to, let's say we need to include an oil phase and a gas phase separately, you can do it. In this white cell, you will come here and select gas or oil. But the 2 first cells, they need to be brines to do this mixing. And this is just a design. This was initially how this tool was taught to be. So I will call it a constraint, but it's also very good to understand incompatibility issues. Okay, so notice that, okay, so for the first brine, select the Olympus reservoir. And for the second brine, select the Titan reservoir. Okay. Now, you will also notice that there is only one white cell here to define the flow. Okay. And there is a yellow cell that is not, you cannot edit this cell. The reason why is because the flow that you need to specify here represents the flow rate of the combination of the 2 fluids. So let's enter here 500 cubic meters per day. And what this means, this 500 flow rate means, is that it should be combined. It's the flow that comes from the reservoir, the first brine from the Olympus reservoir, and the second brine, which comes from the Titan reservoir. We cannot define the flow rates for each one. It will be the combined one, the total one. So once we define that, we go to the conditions, or the conditions grid, where you enter the temperature and pressure. So we know this 100 degrees C and 100 bar. Okay. So once we enter this information, then we go to the conditions tab. And notice that you have, by default, already defined 6 points of mixing from 100% Olympus reservoir to 100% Titan reservoir, every 0.2 or 20% increments. But we can give more resolution to these mixing points. We can go to the steps, to this cell where it says steps. We can change it to 10, for example. And then you click on the button auto step, and that will reset the ratio of mixing to go from 0.2 increments to 0.1 increments, or every 10% increments. Also notice that you have two options of mixing. You can mix by ratio, or you can mix by flow. If we select flow, for example, in this case, so the first point will be 500 cubic meters per day at point 1, and then 0 cubic meters per day at point number 10. But the flow stays constant. Okay? It's 100, 400, that's 500 here, or 500 here. The flow stays constant. It's just how much of one and how much of the other one. For this calculation, we are going to select the ratio option. I think it's more clear. It's like 40 or 80%, or it's more clear to see it that way. Once we do this, then we go to the solids tab and click on the standard solid. So we go ahead and calculate. When this calculates, we can go to the plot tab. But yeah, remember that in this mixing tool, you can only include the brines. And if you want to include the gas and oil, you can bring them, but they will stay at a fixed flow rate. They will not change. They will stay specific flow rate, at the flow rate that you enter. Okay. So this will take probably 20 more seconds. Any questions so far about how to define this mixing tool? Okay. We could take it to the plot and see how it's going. So, okay, so what do we see here? We see again same blue scale intensity versus. Now notice one thing that I want to mention here while this calculates. The first brine that you define in your design tab, which was the Olympus reservoir, that brine will be the x-axis in this plot. And again, we like to plot blue scale tendencies. So let me just move this here. So what do we see here? You will see here that we have two different solids that are above saturation, or yes, super saturated, and then you see other solids that are undersaturated or subsaturated. The two solids that are forming at different mixing ratios are barite and iron sulfide. Okay. And what we see here, also this shape that you see here, this is a typical incompatibility curve, which is this well-shaped curve. And we see for both iron sulfide and barite. And the endpoints of these curves represent the lowest saturation ratios, and the middle points of these plots represent the highest saturation ratios. Okay. So the x-axis, as I said, is the Olympus reservoir. To the right, it will be 100% Olympus. And to the left, it will be 100% Titan. So At ferrite, the red curve, at 100% Titan or 0% Olympus here, has a saturation ratio of around 2.3. And at 100% Olympus, it has a saturation ratio of 1.6. But when we mix these two solutions together, the maximum scaling potential that you find occurs at 40% Olympus, and you have a value of around 3.4. Okay. Likewise, for iron sulfide, notice that there is no scaling risk at 100% Titan or at 100% Olympus. There are not even calculated points for that specific solid. And the reason is because, again, Titan doesn't have H2S and the Olympus doesn't have iron in the composition, so there is no way that we are going to form them. Only when we mix them, we see that now that solid starts to form. Now, when you bring these brines together, you see that at 50-50, 50% Titan and 50% Olympus, you have the highest incompatibility of around 3.3. Okay. So that's what happens. That is how you will see. This will be the trend that you will see as you increase the ratio of Olympus reservoir or brine, mix it with Titan. Now, what happens with the formation of solids? This is just the prescaling tendency. So let's go to the variables button and select, maybe double click on this dominant prescaling tendency to remove the variables, and go to the solid category, and then double click on barite and iron sulfide, then click OK. So what do we see here? We see how the amount of solids for barite, which is this yellow curve here, starts to decrease, okay, as we increase the Olympus water ratio. Now, why is this decreasing? Maybe one reason for this, it could be that as we increase the Olympus brine, if you go and check the composition of the brine analysis for this Olympus brine, you can see that it doesn't contain as much barium concentration as the Titan brine does. So that's why probably this solid decreases. And also you see a similar trend for the iron sulfide. You see that as you increase the Olympus reservoir ratio or the Olympus water ratio, kind of stays more or less constant, but then it decreases. Okay. And yes, this will be the results that you obtain for the solid formation. Maximum solid formation occurs at 10% Olympus reservoir with a value of 30 milligrams per liter of barite. And for iron sulfide, that will be around 1.1 milligrams per liter of iron sulfide. Okay, any questions about this specific tool? Because then we will do the example for oil analysis. But I just want to know if there are any questions for the mixing ratio. If we have time, we will do a second example for injecting seawater into a reservoir. Okay. So yeah, so now we can start with our third example. That will be a bath as well. So far, we have covered the following objects. Basically, all of them. We have done brine, gas, saturator, scaling scenario, scale contour, mixing water, and facilities. The only one that we are missing at this point is the oil analysis. That's why we will be working on this bath as well for the rest of the class. So we will do the same thing. We will do water analysis. We will do a gas analysis. We will learn how to do an oil analysis. then we'll go to create a saturator, the scaling scenario. I don't think that we should do a counterplot. It takes too much time. But maybe we can set it up and then you can calculate it and review the results. Okay. So I see that it's 10:50, 10:49. So maybe we can take another break of 6 minutes and then we can start with this example and finish this so that we don't have any interruptions during the setup of this example. Okay, so maybe let's go back at, yeah, that will be 50, 56. So it will be 10:56. That will be 4:56 for you, Ahmed. And then we can get started with this specific example, okay?
Okay.
Thank you.
What's up?
Back. Is everybody else back? Ahmad, James, are you here? Mike? Somebody? Did I lose everybody?
No, I'm hearing you, Diana. Sorry.
Okay. I am trying to see if Matt is here and James. I don't see signals of them around. Hello. Hi, Matt.
Okay, yeah, Diana, sorry, I'm back.
And what about James?
I'm back as well.
Oh, great. Okay, so let's get started. So we are going to start building this Bathos web. And the first step, as at this point you should know, is to enter the analysis. So let's go and double click on brine analysis. And let's name this analysis Bathos brine. Okay. Before we enter the analysis data, notice in my presentation, I'll show you here. This is the data that we are going to enter for our brine analysis. But notice what I have written here for the bicarbonate ion. Okay, I have written here that for the bicarbonate ion, we should see the alkalinity value. And why am I saying this in this specific analysis? What I am trying to do here is that for this specific water analysis, the total alkalinity was measured, but not the inorganic carbon. The inorganic carbon wasn't measured. So we are going to use the alkalinity value as an initial point for our water analysis. And that means that if you don't have a value for the inorganic, so this will be the initial guess, and then the software will back calculate this bicarbonate value for us. By doing that, what the software is, what we need to do in the software is to use the pH and alkalinity reconciliation option in order to calculate or back calculate this concentration. So let's start entering the data, and I think that you should have it in your spreadsheet. So go to Bathos brine, and every time I do this, I think it's copying anions and cations. Let's see. Yeah. So let's delete this. This doesn't belong there. This will be the water analysis that you should have. So you have mostly sodium, 15,260. Then you have potassium, etc. You also have chlorides. And notice that I have entered a value here of 673. That is exactly the value of the alkalinity that was reported for this water analysis. And we also have some content of acetate, 386. And we have some neutrals as well. Okay. Let me know when you have this information entered in your water analysis or brine analysis. Also, notice here that the cation charge is higher than the anion charge. So there is a positive imbalance here. And to reach electron neutrality, the software added or is adding chlorides, an amount of 408.5 milligrams of per liter of chloride ions. Okay.
Yeah, I'm done.
Perfect. James?
Yeah, I'm ready to go.
Great. So the next step will be to go to the reconcile tab. Okay. So that will be this step here that we are going to do. So these are the measured properties. We say the measured properties that were measured in the lab were pH, alkalinity, and density. And we will enter those values now. So enter. The measured properties were done at standard conditions, 25 degrees and 1 atmosphere. And then let's enter the pH. We said it was going to be 6.7. The total alkalinity measured was 673. And the density was 1.026. For this calculation, we are going to change the option from concentration data only to measured pH and alkalinity. Okay. And then notice we have the alkalinity endpoint pH here. Already, I think I mentioned that before. And we can go ahead and calculate. Wow, it's not running. Is your calculation done? Okay, now it's done. I was stressing out here. Okay, so just to get a more clear picture of what I was trying to do here with the data entry and trying to put the bicarbonate concentration here equal as the total alkalinity. I just want to explain that a little bit more. So notice that the total alkalinity is calculated in the software by as the addition of bicarbonate and the acetate ion. Okay. So we know the alkalinity, the total alkalinity. We know the acetate ion because we enter this value as well. So the software will calculate this for us. Okay. So let's see how much is that. So for reaching the total alkalinity, the software had to add or remove, in this case, it removed a total amount of 66 milligrams per liter of carbon dioxide. So if we convert this into bicarbonate, we can calculate how much the software is removing to back calculate, or removing to back calculate the bicarbonate concentration. Because again, we are adding way too much. We know that the total alkalinity cannot be equal to the bicarbonate concentration. So the software knows that and is removing this amount of CO2. And that amount of CO2 is going to be, this is how I am doing the calculation here just to show what the software is doing in the background. So we have bicarbonate, the molecular weight of bicarbonate divided by the molecular weight of CO2. That gives us a ratio of 1.39. If we multiply the amount of CO2 that has been removed, that will give us the total amount of bicarbonate that is also being removed from the system. That is about 92.82 milligrams of bicarbonate per liter. Okay. That is regarding the bicarbonate. Regarding the HCl, we see that the software had to add HCl, meaning that probably the calculated value was higher than 6.7. Probably it was, I don't know, probably it was 7. And it had to add this much amount to reduce it and mesh and match it with the measured value. Okay. Next, at this point, I don't know if you have any questions. In the report, then you can just go and see the alkalinity, the total alkalinity, but then you can verify the amount of the actual bicarbonate amount that you have in this water analysis, which is 469.2 milligrams per liter. Okay, so now the software knows exactly how much the total inorganic carbon is contributing for alkalinity, and it's also measuring the total alkalinity value that we initially entered as the measured value. So with this, we can say, okay, we have a representative lab sample, and we can move to the next step, which is to add a gas analysis. So so actually in my steps here, it says that it's oil analysis. So let's add an oil analysis. So double click here on oil analysis. And let's change this name to Bartos oil. And we're going to add this oil analysis that is basically going to be mostly a distillation assay. Okay. And if you notice for the oil analysis, you will have 1, 2, 3, 4 different tabs. The 3 different tabs that you see here are ways of entering the analysis, the different types of these are different ways of entering an oil analysis. So you have the combined tab, you have the pseudo components tab, and then you have the assay tab. In the assay option is where you enter the distillation curve, if you have one. This is the one that we are going to learn how to use today, since we have an assay for this specific example. Then you go to the pseudo components. This option is used when somebody already has converted the experimental distillation curve into pseudo components by using a thermodynamic method or model. So once you have those pseudo components, you can simply enter them in here. You can see this grid here. And usually these pseudo components are created by using another program. So we give you the option of entering them here if you already have them calculated. And you also have the option of entering an oil analysis using the combined option. In this tab is where you enter pure component data. In this list that you see, it's a pretty long list. You see mostly alkanes in here, but you can also add down here. If you add here, you will have you can add alkanes, alkenes, alkynes, aromatics, and you can just type in them in here. For our example, the oil that we want to represent has 2 inorganic components dissolved into this oil. That will be nitrogen and CO2 in the composition. So I am going to use this combined tab to enter these inorganic components here. And then we go to the assay tab to start entering the assay data. So in here, scroll down in this list. And now for nitrogen, enter the composition in the oil that is 0.5 mole fraction. And for CO2, the composition is 1.1 mole fraction. So this gives us a total composition of 1.6 mole% of the inorganic components in the oil phase. And we need now to define the other 98.4 mole% of this oil analysis. Also notice that you have a bunch of components here that are 0. They are just taking up space. So what we are going to do is just click on this option that says show non-zero only. And now the list is significantly reduced. You have only nitrogen and CO2, which is the one that has the only ones that have values. And now our next step is to go to the assay tab. So now this assay tab is a little bit tricky. We need to follow specific steps to enter the oil and the assay in here, the distillation curve. So we need to follow 5 different steps. First step is to give it a name. So for this specific assay, let's just name it assay. Okay. And just as a note, the assay name cannot be longer than 5 characters, and it cannot have any spaces within the name. So it has to be 5 letters and no space or a special character. Then we enter 98.4 mole percent, which is the total composition of this assay in the oil. The other percentage is the inorganic components. Okay. The second step now is to define the type of experiment that was performed under these entry options. Okay. So in this case, we are going to select a true boiling point curve experiment. So under type, just click on this drop-down arrow and select PBP curve. The next step is to define the thermo method. So this method is what the software is going to use to convert the experiment into pseudo components. And once those pseudo components are calculated, also the properties of those pseudo components will be calculated. So for this example, we are going to use one of the methods by the American Petroleum Institute that is called API 8. And this API 8 thermodynamic method is going to determine properties such as the normal boiling point, specific gravity, critical properties, Gibbs energy of formation, etc. for all of the pseudo components. Okay. The next step is to define the density of the oil. This happens to be an API gravity oil, and the value is going to be 41. Change this specific gravity to API. Okay, and 41 there. And finally, we define the number of cuts. What this means is that the software is going to take the distillation experiment and break it down into 12 cuts to create 12 pseudo components. So enter 12. Okay, that's step number 2. Step number 3 is to enter the distillation data. Okay, so we have to start typing here the information, volume. We only have the option of volume and temperature. We don't have any mass or mole fraction in here, only volume. So I hear like a very bad noise. I don't know what it is.
I think it was just a telephone, Diana.
Sorry, it's my telephone.
Background, it sounded like.
Yeah.
I see. Okay, so what we are going to do is we are going to start typing here the distillation data. And if you go to the Excel spreadsheet, you will see the option for bathhouse oil. You will see here all the information for that specific distillation curve. Just copy this volume and temperature data. Right click, copy, just paste it here. Okay. So, for example, 1% distilled, the temperature is 26 degrees C. At 5% distilled, the temperature is 41 degrees. And so on until it reaches the last volume percent, which is 100, and the temperature is 397. Okay, so let me know when you have the data in.
Okay, my own is ready.
Perfect. About
Mine as well.
thank you. Okay, so the fourth step now is it's very easy. It's just to use the display, to click on display assay cuts here. So just click on it. And now you will, when you click that button, you will see that the software, it validates your data. It makes sure that you have entered all the appropriate information, and then it will calculate the properties of each one of the 12 pseudo components. So the assay properties table here has been created. Okay, so notice that the software has assigned as a name to each pseudo component as an assay, then underscore, and then the next to it you will see temperature in Kelvin. So this is the temperature at which the pseudo component list, the pseudo component will boil. So again, the name is assay underscore temperature followed by temperature in Kelvin, meaning that that's the temperature at which the pseudo component will boil. Okay. So we see that the first assay boils at 314 K. This is equivalent to 41 degrees C. And notice that this is about, next to it you see the mole percent. This is about 12 mole percent of the total assay. And then you can see the rest of the properties that were also calculated. You see mole, this is the molecular weight. This is the normal boiling point, specific gravity, critical temperature and pressure, and eccentric factors. So if by any chance you want to see even more details about the properties for each pseudo component, you can simply click on the tabs that you see down here. Let's say assay 314, and you will see even more information about each one of those, the properties of the pseudo component that were calculated. Okay, so once that is done, we can go and check on in the reconcile tab. And in here, you can see that we have an assay that represents 98.4% of the total oil analysis of the total crude, and you have also 1.6 mole percent of inorganics. Ideally, normally, we will also be able to put, if you have that information, you will also need to put here the water amount in this oil. But in this oil analysis that was provided to you or to us, it wasn't measured, so we don't see that value. However, since this happens to be a high water cut well, we're going to ignore this mass balance error that is being caused by not having the water amount in this oil analysis. And later in the calculations, we will see if this is really causing a significant error or not in the calculations. Maybe we can back calculate this amount of water and put it into here to make this calculation even more accurate. Okay, so similar to the gas analysis, you don't need to calculate the oil because it will be calculated automatically in the next step. But if you want to go ahead to calculate this, you can calculate, and you will see here some of the results for the reconciliation are shown here in this reconcile tab. Okay, so that is how we enter an oil analysis. Any questions before we move to the next step? Or assay or pseudo components or the combined option? Okay.
Yeah, sorry. Yeah, Diana.
Yes.
Okay, so we don't have to get the water proportions of the assay.
In here we don't. For this specific example, the analysis that was given to us, they didn't report the water.
Yes.
It should be reported. If you have it, that will be ideal. In our case, we don't have it. So we are going to leave it like that because this is a high water cut well. So probably it's not introducing a lot of error. But we will see. We will see with the results and see if we really needed to introduce that water or not. Ideally, you would need to, so that it doesn't cause any mass balance errors.
Okay. So we can be able to calculate that later on.
Yes, and I will show where you see that. Yeah.
Okay.
Okay, great. So the next step that we are going to do is add the gas analysis. And these are just some definitions here for each one of the types, thermometers, densities that we have in the software. That's for future reference. And let's go to the next step. Just double click on the gas analysis and rename it Bathos gas. Oops, I used it wrong. Perfect. Okay, so with this specific well, we know that we are producing gas and we know the flow rate, but we weren't given a specific gas concentration. Nothing. They just said this is how much we were producing, but they didn't let us know the composition of this gas. So just to make sure that we introduce the gas phase, we are going to make this gas something very simple. We are going to make it 100% methane. And there is a reason why we are using this methane for the gas phase. And this is because I want to illustrate the importance of partitioning among the three phases. So for this example, we are going to see how the oil partitions into the gas phase and vice versa, how much of the gas partitions into the oil phase and the water to the oil, etc. So later on, as I just mentioned, we will enter we will see the results for this gas and also the oil analysis in the saturator object. And we will find out what is the calculated gas composition and what is the final oil composition. Okay. So because in here we didn't have to, we are going to assume that it's only 100% methane. Just enter 100% methane for this gas analysis, and we are done. We don't need to do anything else. So another thing that maybe would have been helpful to have is, since we didn't have a gas analysis, it would have been helpful as well to know the water content of this gas analysis. But again, it wasn't given, so we can't really put anything here, but we will back calculate these values if we need to. Okay. So the next step is going to be reservoir saturation. Again, we are going to add a saturator. But before I add the saturator object, for this example, I want to change the units for the upcoming blocks. I want to change the units for saturator, for scaling tendency, for scaling scenario, for contour diagram. In order to do this, I'm going to go to the global level here. Click on where it says ScaleChem training. And once you do that, then go to the units manager. Click on the units manager, and that should bring a new window. Okay. Why am I changing these units? Why do I want to change these units? Probably you are not used to the scale metric units. You are used to the English units. So it makes it easier to enter barrels per day or any other units, Fahrenheit, PSI, or bar G. So I just want to customize specific ones. So let's change the units for the saturator. Instead of having, I'm I already have it in a scale English. Okay, so instead of having it in a scale metric, probably you have it in a scale metric, change it to scale English. Okay. If you, probably because you have my file, you already have this. Change the scale scenario to scale English as well. Change the mixing water to scale English. And which one? What else? Saturated scale. I think these three are good. Mixing water, and maybe the scale contour if we are going to do a scale contour. A scale English. So 4, saturator, scale scenario, mixing water, and contour. All of them should be scale English. If we want to see how the units have changed, you can come here to the options, click on the customize button and go to the parameters. You will see now that the temperature is defined as Fahrenheit and bar G. Okay. And now everything is for example, for thermal conductivity, you have it in BTUs, or partial pressures in bar Gs, volumes in barrels per day, etc. So click OK. And now that we have changed the units, now we can double click and add on the add saturator. Okay. And make sure that now you see here to the right in the summary, make sure that it says scale English. Okay. Okay. Let's change this name of the saturator object to bathos reservoir. Okay. And now, just like in the cases that we have built before, the Titan and the Olympus that we did previously, we are going to do the same general procedure. In here, now we are going to add the brine. That will be bathos brine. Then gas, and then select bathos gas. And finally, that will be the oil. That's the only difference here. We are also adding an oil. That's bathos oil. Okay, for brine, what is the flowing rate? So the flowing rate is 850 barrels per day. For the gas flow, we had that it was flowing at 300,000 cubic feet per day. So enter 300. And this M that you see here under the standard means 1,000. So that's why we're putting only 300,000 standard cubic per day. And finally, you will have the oil that is flowing at 2,200 barrels per day. So 2,200. And that's it. So that's the flow. The next step is to define the conditions at the reservoir. That will be 200 Fahrenheit for temperature and 220 bar G for pressure. Okay. Any questions so far? Okay. So next step. Select the solids tab and also just go to the standard tab in here. So yeah, so you have the standard tab here, and you can just go ahead and calculate here. The button is yellow because we haven't selected any minerals to saturate, but at this point, we have told the software to allow only to, if these solids are super saturated, they can precipitate, but we really haven't instructed the software yet to saturate the mineral, the reservoir fluid with any mineral. And again, the purpose of running this calculation before saturating is because if anything appears to be super saturated, we can analyze it first, and based on those initial results, we can make the decision if we need to saturate or not. So once the calculation is done, go to the report tab to see the results. And let's go down to pre-scale and post-scaling tendencies, and I am interested in the pre-scaling values. And look for anything that is above 1 or equal to 1. So we see calcite is around 75%, and nothing else is really super saturated. I don't see any other values that come to my eyes. No, just 75% calcite. Okay, so it would be reasonable to say this could be this is a sandstone. So I know that I've got some calcite cementation, and then perhaps it's a good idea to saturate the brine with calcite. So if we saturate with calcite, then this calculation will account for maximum risk conditions. So let's go back to the design tab and go to the mineral to saturate. Select calcite, and let's use the standard calcium carbonate inflow to vary. Go ahead and calculate. Okay, so let's wait for this calculation to be done. So again, what this means is that the software will be varying the concentration of calcium and carbonate ions to reach saturation at the reservoir. And go to the report tab once the calculation is done. So in the saturation details, the software is saying, okay, which solid it's saturated, which inflow it used to saturate, what was the initial value of that calcium carbonate, and what is the final value, and what is the difference. So in this case, we have that the software added around 60 milligrams per liter of calcium carbonate in order to saturate the reservoir fluid with calcite mineral. And now we need to see how this changes, or how by adding this mash of calcite into the solution, how this will be reflected in the brine analysis composition. So if we go down to look for the brine analysis composition, brine composition, we will see the following. We see that initially, if you go back to this Bathos brine, the composition or the concentration of calcium was 850 milligrams per liter. And in this case, you see that by saturating this reservoir it increases to only 853 milligrams per liter. This is not a huge change. This is about 0.4% change when I calculated last time that change. And what about regarding the carbonate ions? So when we are adding more carbonates into the water or into the solution, that means that we are impacting the bicarbonate concentration. So that means that it should increase. So if you remember as well, the bicarbonate concentration of the brine analysis that we had here when we calculated, that bicarbonate was around 469 milligrams per liter. Now, by adding those extra carbonate ions in solution, now we see that it increases to a value of 566.5 milligrams per liter. So this will be increasing the bicarbonate concentration of this solution by 14%. So based on these results, we can say that, okay, calcium ion change is very small. Perhaps we are within the sampling or experimental uncertainty. And we can probably think that the bicarbonate also could be kind of reasonable. Okay, so that's good. Additionally, in this brine composition, you see the composition of the methane in the brine. You see how much of that gas is now transferred to the brine phase. The concentration of methane in the brine is around 500 milligrams per liter. And you can also see the composition of the other hydrocarbons, the pseudo components. You see that for assay 314, you have 6.6 milligrams per liter of that assay in your brine analysis. If you go down, you will also see the oil composition. Okay. In this oil composition, the water content, if you come here, you'll see that the software has calculated that the water content in the oil is 0.5 mole %. So this is what the software is saying. You didn't give me a water content for the oil phase, but this is what the software is predicting, okay, at reservoir conditions. Okay. For CO2, it's also saying in my oil composition, I have 0.87 mole % of CO2. And now, if you remember the oil analysis, or no, it was in the gas analysis. No, in the oil analysis. In the oil analysis, we entered that the inorganic component that was reported was 1.1% in that oil composition. And now you see that the software is under predicting that is lower than that value. And the reason is because probably some of the CO2 that was in this oil now is being transferred to the brine phase. Okay, so you see that mass transfer in there, or that partitioning in there. And finally, you can also see here the oil composition, how much of each assay, and the other components. Nitrogen. Nitrogen was initially 0.5, now it's 0.42. Again, probably went to the brine phase. Some of it partitioned to the oil, the brine phase. If you scroll up to find this phase properties table, first of all, you will notice that in here you're seeing only 3 different columns. You're seeing the results for liquid, for solid, for liquid 2. Liquid 1 means brine or aqueous, solid, and liquid 2 means organic or hydrocarbon. There is not a vapor or gas column in here. So what this implies is that the reservoir pressure, at this reservoir pressure, the gas is compressed into the oil phase. Okay, so there is no gas phase. Everything probably goes to the organic phase because it's high pressure. Now, you can also compare the different volumes, the volume at reservoir conditions versus the volume at the standard conditions. In the case of the brine, we see that at standard conditions, it was measured that we had around 850 barrels per day. And at reservoir conditions, we have a prediction of 871 barrels per day. And you see here a difference of around 21 barrels per day. This basically is indicating that some water is being transferred to other phases along the production line, because initially it was higher and now we have lower values at the separator. Okay, and for the organic phase, we have the standard conditions. We are producing around, we have 2,300 barrels per day. And initially at the reservoir conditions, we have 2,200 barrels per day. So we are also seeing a reduction in that volume. And probably this difference indicates that because we are decreasing the pressure, so maybe some gas escapes the oil. Remember that was very pressurized. So the gas escapes the oil phase, and then it causes a reduction in the total volume. Okay, so after analyzing these results, now we can go ahead and go to the next section, which is to calculate the scaling scenario. And let me know if you have any questions so far before we move to the next step. I hope it's all of the assumptions and all of the analysis that we're doing here makes sense. If not, please let me know, and I can make sure that is clear. Okay. Perfect. So now you really should know this. We go scales and we go to click on the actions panel and select a scale scenario. And we are going to get the reservoir fluid from bathos and turn it into here. So we are going to call this bathos production. Make sure that we have a scale English units for this. We should have set them up. Perfect. I see scale English here, so that's good. So next step is just get the bathos reservoir fluid to the bathos production. Okay. This will be whole fluid, bathos reservoir, automatic. And the next step is go to the condition step. Next, we are going to go to our spreadsheet and we'll search for bathos production. These are the different locations. And notice that in here, I'm doing something different. I'm going to make a condition that represents my original reservoir. You know, over time, it will change. So that will be the current reservoir. Maybe the pressure changed. So you see that the pressure is lower, 160. And this will be the flowing reservoir. And then the other locations. Let's copy and paste this. And enter it here under location. So all the mass from the original reservoir goes to every single location. No mass is being lost. And once you have this data, please let me know. The next step will be to go to the solid tab and turn the standard solids on, and then we can go ahead and calculate. Okay. Is all the data in?
Yeah, you can go ahead.
Perfect. So solid. And select the standard solids and click calculate. Then next step, we are just going to analyze our results. And I will show also a different way of analyzing the results, not only using the plot, but also the report tab here. So what you will see here is the saturation ratios and the different locations in the x-axis. You start seeing also here that you have some solids that are undersaturated and some solids that are supersaturated. Actually, the only solid that I see here that is supersaturated is this red line, which is calcite. Okay, the rest of them, they are all below 1. There is really no risk of formation of any scale. So you can see that for the original reservoir, we saturated this with calcite. And you see that the saturation ratio is equal to 1. And then as over time, as the pressure decreases, this is our original reservoir. And as pressure decreases, which is now our current reservoir, pressure decrease at around 60 bar. This decrease in pressure is causing an increase in the scaling tendency from equilibrium to now to a value of around 1.1. And as I continue moving, for example, the flowing reservoir up to the bottom hole, you still see that everything stays slightly supersaturated. And then after you reach the bottom hole, then you see that at 1,600, 1,300, up to, if you go down to the flow line, you see that nothing is being supersaturated. There is no risk of formation of calcite in these locations until you reach the saturator, where you will get slightly supersaturated again at around 1.1. As I have been mentioning, it's ideal also to see how much solids are being formed. So you can just go to the variables. And if you had in the plot template manager that specific plot, you can just click on it or go to variables and make sure that you have, sorry, that you have the prescaling tendency for the y-axis. Give me 1 second, I need a little bit of water. Oh, I don't know what happened. Okay. So make sure that you have here the prescaling tendencies and the solids in the y2 axis. Once you have that, you see here that over time, like if we focus only on the formation of solids, so that's the solids will be here represented by these square data points. So all solids will be precipitating out at current reservoir, flowing reservoir, and bottom hole. Nothing really will precipitate out during these locations. The maximum amount of scaling risk that you will have is 33 milligrams per liter. And then you will also have some formation of solids at the separator. Okay, and that will be around 21 milligrams of calcium carbonate precipitating out. Okay, so, but we are sick of this plot. We don't want to see this plot anymore. So one other way of analyzing the results is to go to the report tab, okay? And in here, you will see the information of every single location that we enter. You will see the same plot, the same reports that we have seen before, phase properties, prescaling and postscaling, brine composition, etc. Okay. If you want to see more information, you go to the customize button. And if you want to see the scaling scenario summary, you can just leave it and other information. I don't want to see the inlet summary, so I'm going to uncheck that and then click OK, because I don't want this to be super long. And what we are going to do now is that I want to basically compare the results that we are obtaining in the simulation at the separator and compare it with the actual measured values at the separator when the samples were being taken, okay? So to do that, let's go down, scroll down, till you find the location that says separator. Oops. Okay, it should be the last part. So I saw it here. So you see location name, separator. Okay. Once you get there, now you will notice that the software is computing that there are 4 phases that are being formed at the separator: brine, vapor, solid, and organic. So since the flow of the different fluids were measured at the separator, I just want to make sure that the software is predicting the same measure values. So let's start with the brine or liquid phase. So we see here that the software is predicting that we are producing around 849 barrels per day. And if you remember, when at the separator, it was measured a value of 850 barrels per day. So this is a really good estimation. We are really, it's a good value. It's almost matching the value that was measured at the separator. what happens with the organic phase. The organic phase, for the organic phase, the separator is, the organic phase is, the software is calculating 2,214 standard barrels per day versus the 2,200 barrels per day that we measure, the 2,200 standard barrels per day that were measured. So again, we are off like by 14 standard barrels per day. So it's not that, this value is fine. Now for the gas phase, for the gas phase, we are predicting 275,000 standard cubic meters per day. But we originally measured that we were producing 300,000 standard cubic meters. So we are maybe off by about 8% here. And what is causing this discrepancy? What is causing this discrepancy is that we assume that we had only methane in the gas phase. And we also didn't have any water content or CO2 content or any of the pseudo components or the oils that were being produced with that gas analysis. So an 8% difference, that's not that bad. But let's see how much the software, if you go down, let's see how much the software predicts that the gas composition will be at the separator. So the software is, if you go down and go to the oil and gas composition table, you can see that the software computes the composition of both oil and gas at the separator. And this table will give you an idea of the composition that you should probably have measured if you are not given one. Okay, so this gas, for example, the gas composition will have, let's say, what is water? Around 2% water in the composition. Okay. For the assay 31, for example, in the gas composition, you should have this composition of gas, of this assay in the gas. And for methane, let's say methane, this will be the real composition. It wouldn't be exactly 100%, it will be 86. And the same for the oil phase. This will be the composition of the assay in the oil phase of the separator, and this will be the composition of 0.2% of water in the separator. Okay, so any questions so far? I think that with this, we are good to just go ahead and do a really quick scale scenario, a scale contour, and then we'll be good. But I just want to address any questions if you have some. Because we only have 6 minutes left.
Okay, hello, Diana.
What was that, Ahmed?
Yeah, okay, I have a question here.
Mm-hmm.
Okay, if I'm trying to do scaling prediction using the ScaleChem,
Mm-hmm.
what analysis do I need? Is it must I have brine analysis, gas analysis, and oil analysis? Or maybe it's only brine analysis can be able to predict to some extent the scaling tendencies.
Oh, yes. If you only have the brine, let's say, and you have only this brine and you enter your compositions, in the report, it will tell you if you will have some scaling. Based on that brine analysis, you will have some scaling risk. So if you notice here in the Olympus brine, it was telling me right away that I will have a problem with calcite because I have a saturation ratio of 6. But I will not have any problems with anhydrite. Okay. But if you have all of the other analysis and you really want to make sure to have a representative fluid at reservoir conditions, so it will be ideal to have the gas and the oil analysis. Not always that's the case. Probably it's not always the case, but that will be ideal because if you have the composition, let's say in your gas analysis, you know that you have CO2 and H2S. So that will be having an impact on the acidity of the brine, because they will partition. You know, the CO2 will partition and it will dissolve in the brine. It will have a peak of impact. So probably this calcite now will decrease to a prescaling value of 2. Now, if you and your oil analysis also have also some CO2 dissolved in that oil analysis, or maybe you have some water content. So then that water content is going to dissolve, let's say, it kind of, as you decrease the pressure, so you increase the amount of water that goes up because it was initially compressed. I don't know, probably that could be a case. So that will dilute your brine analysis sample, and probably that won't give you a representative prescaling value or scaling risk. So the answer to that is, ideally, it's better to have the oil analysis and gas analysis, but with the brine analysis, you can, it's a good starting point to analyze if you will have some scaling risk or not. But it's important to understand that there will be mass transfer effects, partitioning effects, all of that, and that will also have an impact on the final values for the scaling tendency. I hope that answered your question.
Yeah, thank you for that.
No problem. So I think that we can leave it. We can stop here. My next example just was going to go through scaling contour, but I guess if you want to do that part, I have it in the manual. And the last example I wanted just to introduce, but we already covered this mixing water tool. I just wanted to show you how to do an injection water mixing using the bathos reservoir. But I will also provide this slide so that you can do it. But with that, I think that that was mostly, that was what I was going to talk about today. So if you have any questions, I will always be here. This is my contact information. And if you have any problems with the software, you can always contact OLI that support that OLI systems. And yeah, thank you for your time. And it's been a pleasure working with you. And I'll give it back to Mike.
Yeah, thanks, Diana. Thank you guys for joining us. Appreciate it. I know it's a lot of a day to take out to look at something new. Everybody's got enough work on their plates already, so we appreciate you taking the time to look at closer at OLI. The one thing I'll remind you of beyond keeping us in mind, so if you do have a 30-day copy of the software now that you can use on your cases, we do request, because it's a free copy, that you don't use them on live active projects, but definitely in terms of evaluating how well OLI fits into your applications and your project needs. Make use of it, try it out. Let us know if you have questions. Definitely don't spend a lot of time beating your head against the wall if you're running into trouble. Diana's here. The rest of our team can help as well. So we want to make sure that you get a lot of value out of the 30 days and really can put the software to the test on your particular applications. So encourage you to do that. Otherwise, just appreciate everybody taking the time, and we will look forward to hearing from you as you go through some other calculations. Let us know how we can help.
Thank you very much, guys.
Take care, everybody. Good to talk to you.
Yeah.
Talk soon.
Thank you very much, Mike, Dana,
Bye-bye.
Jeff. Yeah. Bye.
Bye.